Hey, McLaren here with McLearn, launching the channel with this video. I'm pretty excited. So welcome. I want to teach you all about number systems today. You may have heard of something called binary and asked yourself, what is binary? Or you may have wondered, why do we count to 10? It doesn't have to be that way. I want to use this visual to help you understand why we count to 10 and how that works and some alternatives. It's kind of cool. It's kind of pretty looking if you look through here. I'm just going to kind of fly around so you can kind of check it out. You may ask yourself, what patterns arise? So this isn't just art. This is math, yo. For real. Like, there's a lot of math going on here. It looks very similar at first right here. We're at 1, but as we go down here, we get to higher numbers. These guys start looking a little different, huh? So if we go over to, let's say like 15, these all look pretty darn different. But what's similar about them? If you count them, there's 15 of these in every single one of these, so if you look, that's 10 high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 there, and 5 there. 15, right? And so if I look here, same height. Oop, there we go, come on. It's the same height, so it's 10 tall, but now we've got 6. Like now we've got 7. So this is base 10. These white clear glass blocks, this is what you're familiar with thinking when you're thinking of like numbers. You're used to thinking, well, I add one more block each time I go up a number until I get to 10. Then that group is full and you need to start adding to another group there. So like you can see like, okay, I've got one group of 10 here, aka that right there. And I've got one group of 1 right there. So 11, yeah? So this is what we're used to thinking in, but we don't have to be doing it that way. There's tons of other ways to do number systems. So for example, it's kind of easy to compare right here. But if we had 9 be a complete set in the ones place, then what we normally think of as the number 10 is one complete set plus 1. So in base 9, this would be 11. Even though it's the same number of blocks, you could write it as 1 in the next place value, because we've got that complete set, and 1 in the next place value, yeah? Or in base 8, the same number would look like this. It's the same number. I know you want to say that's 12. It's not 12. 12 is in base 8 looks like this. Because we've got 8 plus 4, right? 8 plus 4 is 12. So that would be what that would look like. So on and so forth. Another example that I think is pretty easy for people to grasp is base 3. So if we look here at base 3 here, 1 is still 1, 2 still looks like 2, 3 still looks like 3, but now we've got a complete set of 3. And so we've got one set of 3 and one single by itself. So this is what 4 in base 10 looks like when we're in base 3. 5 in base 10 looks like this. And then something weird happens here is that we've got 2 complete sets. So basically, you can't write the base number in a single spot. You have to carry over. So when I have 3 here, that means I need to go over to the next place value, right? So on and so forth. If I got 2 sets of 3, I've got 2, and then I've got a single 1. I've got 2 sets of 3, and I've got 2 there, so it's 22. And then this is actually interesting. This is what 9 looks like in base 3. So we've got a 3 by 3, which it looks kind of like what we would normally call 100. And you can call this in base 3, it gets kind of confusing to think about this way, but this is like not the ones, tens, and hundreds place. This is more like the ones, threes, and nines place. It's because every time we have 9, we add 1 to the nines place. So we've got 1 nines place and 1 ones place there, and so on and so forth. I'm just gonna skip up a couple. So if we've got here, we've got our 9 here, plus we've got 2 sets of 3, so we've got 1 nines place and 2 threes place, so on and so forth. And then you can imagine that here we've got 1 set of 9, we've got 2 sets of 2, and we've got a 2 sets of 1. So this is really close. So you can imagine, I mean, it's pretty easy to imagine what this looks like when we add 1 more. We've got 2 sets of 9. So this would actually be 200 if we were to do this next number, right? So that's base 3. Now here's the one that you all probably have been wondering. If you clicked on this, you're probably like, well, what about binary? Get to binary, right? So binary is, you've probably seen it before with like ones and zeros, but you haven't really understood what it is really. Binary is just like base 3, but instead of not being able to go up to the number 3 before going to the next place value, you can't go over 2, or you can't get to 2. So you can't write 2. You can have 2 in a group, but yeah, so on and so forth. So we've got 1, looks very similar. And then this is a complete set, so we have to write it as 1, 0. We've got kind of like the ones place, the twos place, so we've got a 2 and we've got a 1. And then we've got, in this case, you can't have 2 sets of 2 because you can't go up to 2 in base 2. So this is the 4's place. So we've got a 4's place done. We've got a 4's place and a 1's place. So 4 plus 1 is 5. And I'm just going to go up to this one because it's kind of interesting. When we get this cube, how many are in that cube? Count that out to yourself, right? 8. So we've got no 1's place, we've got no 2's place, we've got no 4's place, we've got one singular 8's place. Then if we've got our 8's place plus 1, that should be 9, right? 9. And then I'm just going to go to here. We got our cube, our 8's place, and we've got our 4's place, right? So we got 8's place, 4's place, 2's place, and 1's place here. So we've got 1 8, 1 4, and no 2's and no 1's. So as you probably did that mental math, we've got 12, right? It's kind of interesting. If you compare these, we've got 8 here and then 4 there because we got 8's place and our 4's place. But if we look at it here, it's kind of weird because now we're in base 3, remember? We got our 9 here in that place, and we got our 3 here, our 3's place, so it's written like that. So these, although they're the same number, they're written very differently. It's kind of interesting. And you might be asking yourself, well, what are the trends between all these number systems? I mean, it's kind of cool to kind of see them like this. There's a number of trends. I would like to show you in a spreadsheet, but I want to also show you it here. So I also just want to really quick show you if we've got, and I do want to say this is not the only way to show base numbers. There are other ways of doing it visually. This is just kind of how I decided to do it. So here we've got, you might say, well, I've got 2 cubes, right? But remember, we can't have any 2's of anything in binary. So what we've got is that you can call it like a row of cubes. So we've got our row of cubes here. So if you count this, there's 8 here and another 8 there. So that's 16. So this is our 16th place. So 1's, 2's, 4's, 8, and 16th place, right? So we would write this as, we would write 16 in binary as 1 0 0 0, 0. And then 17 would look like that, right? So I want to show you all some trends. Obviously, the first trend that jumps out to me is right here. 1s all look the same, 2s all look the same. 3s start looking different, but from here on out, the 3s look the same. And then 4, they all look the same here. 5, they all look the same there, but not here. And so you can kind of see if we go diagonally, these are the same all along this diagonal to the left. If I look here, just to help you kind of see, all these are the same, those are the same, those are the same, those are the same, so on and so forth. But if we look to the right, they start looking a little bit different there, right? So that is our first little trend that jumps out to me. There's a couple other interesting things going on here. Is if we look at the 11s, or not 11, the 1-1s in all the base systems, they also kind of follow a similar trend. So all of these are, if we look at what they look like written, those ones that we were just talking about, that diagonal, they all are 1, 0. So that's 1, 0, 1, 0, 1, 0, right? Hi, zombie. So on and so forth. So you can imagine all of these are 1, 0 because they've all got a full base. Now, if we go up 1, the 11s are also in a row. So if you look here, you can kind of just see it visually that there's one ungrouped as we go down, yeah? And so we've got those 11s there, and then we've got 12s here, or not 12s, the 1, 2s, and they're kind of going diagonal as well. And 13's got its 1, 3's going diagonal from it as well, so on and so forth. So we got all these guys doing these diagonals, and then there's also an interesting kind of trend with the next place value. So that's like, let's see, where is it? I think it's this one. Yeah, no, that's the 1000s. I want the 100s. So we got 100 here, which you might think, oh, maybe 100 is over here. No, that is not the case. 100 is right here in binary. But to get to 100 in trinary, I think? I'm not even sure if that's what you would call it. You'd have to go all the way, not all the way, where is it? Right here. So remember, 100 is kind of like a wall, right? So to get a wall of 3 by 3, we have to get to 9. So we were here, we're at 4. To get to 9, we had to go all the way here. And if you're knowing your exponents, you're familiar with that, then you might be seeing a trend. We've got 4, we've got 9, and then in base, what is this, base 4? Yeah, base 4, it would need to be 16 to get to that 100. Yeah, look, 16 right there. And of course, these things start getting more spaced out as we go further and further. So to get for base 5 here, it would need to be 25. So we would need to be going all the way out there, yeah, to even get to its 100. In other words, to get a 5 by 5. Because we've got 5 tall, we need to go another 1, 2, 3, and then another 5. So we need to go another 8 over, aka 8 plus 17 is equal to 25, right? So yeah, not only is this pretty, but we can look at these number systems comparatively and see some cool little trends. Now I would like to show you what this looks like in a spreadsheet because it helps you see the bigger picture all at once. This is kind of pretty, and fun to fly around. Honestly, I really enjoy flying around in this, but I did want to show you the spreadsheet as well. So I'll show you that in just a second and reiterate some of the things we pointed out earlier. Oh, actually, one more thing. I wanted to do a little fade out between this and that. So if we look at this and we go up, get the numbers up there. We've got the numbers, remember, right there. And we got all of these are the same number, and these are different base systems. So this is basically laid out like how my my sheets is. So I wanted to line them up to best transition between the two. All right, I'll see you in a second. All right, so we've got our number of things, which are just like, you know, objectively the number of blocks that we have right up here. And then we've got the different base systems that we're looking at right over here. So remember, 1, no matter what base system we were at, was looking like that. And then 2's all look the same besides in binary. 3's look the same besides in trinary and binary, so on and so forth. So all of these guys look the same. And then we were looking along this diagonal here, and all of these guys over here were the same. But then when we were going higher, it started getting a little bit different. All the 10s looked the same, all the 11s looked the same, all the 12s looked the same, so on and so forth. But as you can see, these kind of start jumping up where they start up, because, well, you can't have 1, 4 in base 4 because, well, 4 is not allowed, right? Or like 1, 3, you can't have that in base 3. Or 1, 3, you can't have that in base 3, right? So we got those going on there. But what I really wanted to show you is what's really kind of nice from this eye in the sky perspective is that you can see how the 100s and whatnot get spread out. So if we look at our sets of 2, so when we had 2 columns next to each other, they followed this pattern where you could see them there, 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 and you can see it goes over 2 and up 1, over 2 and up 1 for base, or 2 sets of whatever it is. So remember, like 14 here, you've got 2 sets of 7 there. So when you're writing it in base 7, it's 2 in the 7's place and 0 in the 1's place, so on and so forth. So it follows that pattern, right? And then if you've got 3 of whatever the base number is, like if I've got 4 and I've got 3 sets of that, that'd be 12, yeah? But you can't have 3, 0 in our trinary system here, because remember, 3 cannot be in a place value for that. So they have to, this has to start here, kind of like how 2, 0 started in trinary. So, but this also then follows the pattern of it going over 3 and up 1, over 3 and up 1. And you know, I didn't fill all of these in, but I know the pattern, so I know where it's going to be. So for example, if I've got 3 sets of 7 here, that's 21. And it's following that same pattern, so on and so forth. And then also base 4 has to start when we're in, or not base, if we've got 4 sets of whatever the base is, such as base 5, then we've got 20, and that has to start in base 5, because base 4 can't have 4 there. And this one, instead of going over 3 and up 1, this goes over 4 and up 1. So you see that little pattern there as well, which I thought was kind of cool. And then we've got our next thing, which was, I thought was interesting. This was when we had like our squares. So remember, in base 2, that square was a 2 by 2. So we've got that 100 there, and then this goes over 1, 2, 3, 4, 5 and up 1. And then this doesn't go up over 5, it goes over 1, 2, 3, 4, 5, 6, 7, and then up 1 to get there. And then keeps on going. I think, oh, I forgot to do the color on this one. This should be colored like that. So you can see those that are similar. And then I think I also messed this up. These were the cubes. So a cube in base 2, that's 8. Remember, we've got our 1's place, our 2's place, 4 place, and 8 place. And that looked like that little cube, yeah? And then we had all kinds of interesting stuff going on there. So our cube for this one, for base 3, would be 27. So on and so forth. And then this keeps on getting spread out even more, kind of like how those 100s are getting more spread out as you go up. The 1000s are even more spread out between them. So if we were trying to get to, I think that this is base 4, if we were doing that, that would be 4 up to the 4th power, which is what, 64, I believe. So we've got 4, actually, is it 64 or is it 128? It's really far out there. So we've got 4, 16, and then I think 64 is the third one. So actually, no, it's 64. Yeah, it is 64. But as you can imagine, then it keeps on going even further out. So I thought that would be kind of interesting to look at all the trends at once using this color coordination. If you'd like to see more videos with the array, or if you've got questions, please let me know. I'd be happy to answer some of those questions or even do a follow-up to this. I also was thinking of doing some other topics using Minecraft, essentially like base 10 blocks, because there's a ton of stuff you can do with base 10 blocks, and Minecraft has the benefit of giving you infinite blocks, because that's the one problem with base 10 blocks, is that you're set by how much you have in the kit, and that really limits you. But Minecraft doesn't have that problem. So if you'd like to see more, please subscribe, like, and share, because I would love to do more videos like this, but it takes a fair amount of time to set up, and I would like to know how much interest there is in weird Minecraft math, you know? In any case, thank you for joining me. This has been McLaren with McLearn.